Okay, so I don't know, I left this out here. Antiderivative notes, not antiderivatate notes, or whatever it said. Okay, so we've done a lot of derivatives. That means you had the function, and the question said, find the derivative. Now we're going to go backwards, and they're going to give you the derivative, and we have to find the original function. So that's called the antiderivative. So taking the derivative is you get the derivative. Antiderivative is you have the derivative, and you're trying to find the original function. So we did that a little bit yesterday, right? We had 3, and I said find a function whose derivative would be 3. So what was that? 3x, right? The derivative of 3x is 3. So if I give you 3 and ask for the original function, then it's the antiderivative is 3x. Okay, but then yesterday we learned a really sly way to find the antiderivative. What was the sly way to do it? Just slap that integral sign on the thing, right? Okay, so here's my derivative, and I need to find the original f of x. So the first answer is you can just do this. Yes.
Can you explain why they're not x's and why they're t's?
Because we want this function, we want the input to be there,
Okay.
not here. So we need them to be different variables. Yes?
And that 4 is just random again?
So yes, Dan is reminding us that this could be any number, and it would be okay. We could make that 100, we could make it 8, we could make it -7, and it still would be a fine answer. Good. The theorem had an A there, meaning it could be anything. Okay, so the reason this works is if you take the derivative of this, in other words, if you put a d dx in front of this, then it'll get rid of the integral sign, and you'll be back to the original function. Okay, so this is the sly way to find the antiderivative. Okay, but we'd like to find an actual formula, because this is kind of messy to work with sometimes. As you found out last night, this is a kind of a nasty formula to work with sometimes. So it would be nice to have another answer where we had the actual formula without an integral in it. I don't want us to forget about this. This is important knowledge. It's the fundamental theorem of calculus, but we'd like to have a nicer formula than that. Okay, so when you take the derivative, the power rule says multiply the exponent in front and then subtract 1 from the exponent. So if we're going to go backwards, instead of subtracting from the exponent, we should add to the exponent. So if we have x cubed, we should make it x to the 4th. So when you take the derivative, you subtract 1 from the exponent. So when you do the antiderivative, you add 1 to the exponent. Okay, then also, you multiply by the exponent when you take a derivative, right? So when you go backwards, you should divide by the exponent. So there's the antiderivative of x cubed. The 4 would just hang out because it's a constant, right? Then if you took the derivative, it would be 4x cubed over 4, and then the 4's would cross out, and you would just have x cubed. So we're good. We're successful so far on the x cubed part. Everybody okay with that? So now we're just going to keep doing backwards power rule. Add 1 to the exponent, divide by the exponent. The 3 is just hanging out because it's a constant, right? So add 1 to the exponent, divide by the exponent. add 1 to the exponent. When you add to a negative, it makes it -1 instead of -2, right? Add to the exponent, divide by the exponent. Everybody good so far? Add to the exponent, divide by the exponent. Uh-oh, that's not good. Everybody see the problem? Better erase that before somebody walks in. Don't want anybody seeing me divide by 0. So backwards power rule doesn't work on this. The reason backwards power rule doesn't work on this is another way to write x to the -1 is 1 over x. What's the antiderivative of 1 over x? Natural log of x. Isn't the derivative of the natural log, isn't that 1 over x? It's not quite as good in your head as some other derivatives, right? But the derivative of natural log of x is 1 over x. So if you have the antiderivative of 1 over x, then it's the natural log of x. And then I could put +7 here if I wanted, because the derivative of 7 would be 0. Or I could put +99. I could put any number here, just like I could put any number there. Okay, so this is the antiderivative. It's the antiderivative using an integral sign. And this is called the explicit antiderivative. So if the question asks for an explicit formula, it's basically saying you're not allowed to do it the sly way. And then sometimes it'll say, give me an antiderivative that uses an integral sign. And then they're saying they want this. Both of these are very valid antiderivatives. Probably I would rewrite this as 1/4 x to the 4th. And then I would cross out the 3's and write plus x cubed. I'd probably change that to a minus, and then I wouldn't have to divide by -1. But you all get that, so I don't need to write it down. Okay. So now for example 2, I'm going to have the derivative equal cosine of x. And I want to find all possible explicit antiderivatives. Find all possible and explicit antiderivatives. So since it says find the explicit antiderivative, that means I'm not allowed to just slap an integral sign on it and get an answer. So what is the antiderivative of cosine? Just regular sine, right? Because the derivative of sine is cosine, so the antiderivative of cosine is sine. Then I could plus any number I wanted, right? So in order to tell the reader that I can plus any number, the tradition is to write plus c. And that c just says, hey, it could be plus anything. It could be plus 7, it could be plus 99, it could be plus whatever. I'm here to tell you that you're going to forget this several times in the next month. I will probably forget it once or twice in the next month. So just try to keep at a minimum how many times you forget it. When you take an antiderivative, you've got to write a plus c. Okay, but sometimes you get extra information besides the derivative. So here's the derivative. And then sometimes they give you some more information. Like that. And then they ask you to find the original function. Okay, so the derivative is e to the x. So what's the antiderivative? E to the x, right? Because the derivative of e to the x is e to the x. So that means the antiderivative of e to the x is e to the x. Okay, so original function is e to the x. Don't forget plus c. Okay, now this information here is going to allow us to figure out what c is. So if I didn't have that piece of information, there would be infinitely many possible answers. But then with this piece of information, that gives me a specific answer. So I know that when I plug 0 in for x, based on that information there, I know that if I plug 0 in for x, it's supposed to spit out 9. In other words, if I put a 0 where the x is, then y is going to be 9. So then e to the 0 is 1. And then to figure out c, I just have to subtract 1 from both sides. So c comes out to 8. So then your final answer is that the f of x is e to the x plus 8. Yes?
Wouldn't it also be after the x equals 9 e to the x plus 0?
No, because the derivative of 9e to the x is 9e to the x. So that would be, your answer would be the answer to this problem. Good. Good thinking. Is everybody okay? Okay, so when you have a problem like that just asks for the antiderivative, there's infinitely many answers. So you put plus c to specify that. But if you get one piece of information, then you can figure out what the c is and get just one specific final answer. Okay. We all know that if I were to let go of this marker, it would start falling. So what is its velocity right now? The velocity right now is 0, but then if I let go of it, it's going to start moving, so its velocity is not going to be 0. So its velocity will change if I let go of it. What is the change of velocity called? Change of velocity is called acceleration. Okay, so if I want to change the velocity, all I have to do is let go of this. And that'll cause it to accelerate. The derivative of velocity is acceleration. So the change of velocity is called the acceleration. Okay, so if I let go of this, it will start accelerating. Why? Because of gravity, right? Perfect. So because this thing will start accelerating because of gravity, so it's called acceleration due to gravity. Okay, so there is acceleration due to gravity. We all knew that. We just don't usually call it that. But what we're saying is that something will speed up because of gravity. Okay, now on Earth, things speed up more quickly than they do on the moon. There's a stronger pull of gravity on Earth than there is on the moon. So we need to know the specific acceleration due to gravity on the Earth. And it is negative 32 feet per second every second. So what that means is, when I let go of something, it will speed up 32 feet per second every second. So in other words, if I let go of something, 1 second later, it'll be traveling 32 feet per second. And then 2 seconds later, it'll be traveling 64 feet per second. And 3 seconds later, it'll be traveling 96 feet per second. That's true no matter how heavy the object is. Bowling ball will speed up the same amount as a feather if there's no air. So to simplify these problems, we usually say there's no air. If you haven't seen a video of a bowling ball and a feather being dropped with no air, you should YouTube search that, because it's pretty freaky to see the bowling ball and the feather fall at the exact same rate. It's true. If there was no air in this room, the bowling ball and the feather fall at exactly the same speed. So that's why this number doesn't have anything to do with the weight of the object or the aerodynamics of the object. Okay, so on Earth, things will speed up 32 feet per second every second. The negative just means that it's going to pull them in a downward direction. So for all these problems, down is negative and up is positive. Just like on a number line, this way is positive and left is negative. Okay, then we also need to know the metric amount, and the metric amount is negative 9.8 meters per second squared. Okay. So let's say a stone is dropped. So this is example 4. From the top of a building. That is 450 meters tall. And for part A, the question is, how long will it take for the stone to reach the ground? Okay, so the question here is asking about the position of the stone. It's saying, how many seconds is it going to take to get to a particular place? So in order to answer this question, we need the position function. S of t is going to be key to this problem. But we don't have information about S of t. All we have information about is acceleration. We know the stone is going to accelerate in this way. So this is in meters, so we need to use the negative 9.8. So the acceleration equation for this problem is negative 9.8. So we have an acceleration problem, an acceleration equation, but what we really need is a position equation. How are we going to get a position equation from an acceleration equation. Yeah.
Can we take the antiderivative two times?
Yeah, we're going to take the antiderivative twice. Because when we have the position function, the first derivative is the velocity, and the second derivative is the acceleration. So if we have acceleration, we antiderivative once and we'll get velocity, and then we antiderivative again and we'll get position. Okay, so if I take the antiderivative of this, that's going to give me my velocity equation. So what is the antiderivative of negative 9.8? Negative 9.8x, right? Just like yesterday, the backwards derivative of 3 was 3x. So the backwards derivative of this number will be this number times x. X is actually slightly wrong because the variable is t. So it should be negative 9.8t. But you guys were thinking good, and I didn't want to shoot you down right away. Xt, it's the same thing, basically. We forgot our plus c. I told you were going to forget it. Maybe some people were whispering, but it should be there. Don't forget plus c when you take an antiderivative, right? So we're going to need to figure out what this c is. So let's look back at this problem. What allowed us to figure out what c was? That information right there, right? So in order to figure out c, we need to know a point that's on the graph. So in order to figure out the c here, we have to know a point that's on the velocity graph. So do we know the velocity of this stone at any particular time? Yes, Rebecca, what is it?
0 at 400.
When the position is 450, the velocity is 0. Good. What's the time then?
0.
When the time is 0, the velocity is 0. In other words, at the beginning of the problem, when time equals 0, right at the moment when the stone gets dropped, the velocity is 0. Okay, so we know that v of 0 equals 0. And Rebecca brings up a good point. We also know that the position then is 450, and we're going to use that later. Does everybody see where this came from? Are you sure that you see why it should be there? That was the first bad joke of 2016, I think. Or maybe I told one already, I don't know, but we'll have to go back and look at the tape.
Positive one, the other than.
Oh yeah,
Positive.
I asked if you were positive. Yes, good. So it's the second bad joke of 2016.
I can see.
Yes, you see. All right, so anyway, we can use this piece of information to figure out what this c is. So we know that if we put a 0 in for t, this is supposed to spit out a velocity of 0. I would recommend that you write this step down, even if you think you know what the answer is ahead of time, because it's good practice. Because on this problem, it wasn't easy to see what the problem was going to be. Okay, but on this thing, c clearly comes out to 0, right? Because negative 9.8 times 0 is 0, then you subtract the 0 to the other side, and you get 0. Okay, so now we have a solid velocity equation. The velocity at any time is negative 9.8t, which makes complete sense, right? Because I told you that it was going to accelerate 9.8 meters per second every second. So if 3 seconds have gone by, it will have accelerated that 3 times, and so then its velocity is going to be 3 times that. 3 times that. So that makes sense from what we already knew. Okay, but really I need the position equation, right? So I got to go antiderivative one more time. So the negative 9.8 is just a constant, so it's just hanging out. And then I need to add 1 to the exponent. The exponent used to be 1, so now it's 2. And divide by the exponent. When you're doing backwards power rule, you add 1 to the exponent and divide by the exponent. And don't forget plus c, of course. This c is a different c than that one. So if that bothers you, you could call this one C1 and this one C2. Or you could call this one C and that one D. I just call them both C. It doesn't bother me. Okay, but we need to figure out what this C is. And so because of that, we're going to use what Rebecca told us. We need a point on the position function. So do we know the position of the stone at any particular time? Yeah, we know at the beginning of the problem, at time 0, it's at a height of 450. So that tells us that S of 0 is 450. So I can use that piece of information to figure out that C. These weird dirt marks on here. All right. Okay, so I know if I plug in 0 for t, are you okay if I divide the 9.8 by 2? So if I put a 0 in for t, I'm supposed to get 450 out on my position function. So C comes out to 450. So then my solid position equation is negative 4.9 t squared plus 450. Now usually somebody in the class, maybe 2 or 3 people, are thinking, I can skip this step because I know that the C is always going to be the number that you get when you plug in 0, right? Like see how 0, 450, so then you just make this 450, and 0, 0, so then you just make this 0. Watch out. This 0 spit out 9, and C wasn't 9. So that's why I said I highly recommend that you write this step down, even if you think you know what the answer is ahead of time. Okay. So there's my position equation. Oh, so yes, go ahead, man.
But logically, like, wouldn't the position at 0 always be the same?
No, not here. If this is your velocity function,
Okay.
your position at 0 is 9, even though your C is 8. It's just because that's a polynomial, and when you stick a 0 into polynomial, you get a 0 out. Good. Okay, so we have our position function. We haven't even answered the question yet, though, right? The question is, how long is it going to take for the stone to hit the ground? So this is going to sound like a trick question. How high is the stone when it hits the ground? It has a height of 0 when it hits the ground, right? So when I ask the question, how long is it going to take to hit the ground, I'm really asking, when is it going to be at a position of 0? So when is it going to be at a position of 0? That's a summary, that's a mathematical summary of what those words say over there. Okay, so that means I need to figure out when this equation will spit out 0. In other words, when will the position be 0? And that's pretty easy to solve. You just subtract the 450, divide by the negative 4.9, and square root. So look up what that comes out to. So 9.583 seconds. So you were checking if your physics equation worked on that? Is that what you're?
No, I was solving for it, and then my calculator decided to restart, so I lost all my.
Ridiculous. Ridiculous. The calculator has it out for you, I think. Okay, is everybody okay? So this is how long it's going to take. It's going to take 9.583 seconds for it to hit the ground. Is everybody good? Okay, that's all I got for today.